Hello. Welcome back, everyone. Now we have Professor Pavan Kumar from ICTS Pune talking to us about Brownian colloids.
Thank you very much. At the outset, let me thank Ranjini and Mahesh for organizing this particular workshop, plus a lot of other things related to the workshop. I'm delighted to be here at ICTS as always, and I'm also thankful to a lot of people who are giving very interesting talks. I am looking forward to join both really and virtually, so that is another thing. To just give you an overview of what I'm going to kind of talk about, and also something related to what we have been doing in my lab for almost a decade or so. Before that, kind of shout out to some of the stuff what I'm going to discuss. A lot of content, especially if it is connected to some historical aspects of the work. Yeah, I would urge you to just look up my blog. There's a lot of stuff which is there too, so you'll be able to explore things. Also, some stuff is also there on our lab's YouTube channel, including a podcast. And by tomorrow, you will probably be able to hear one of the episodes in which one of the organizers of this meeting, I'm not going to reveal who it is going to appear on the podcast, which is already pre-recorded, by the way. Okay, so what I'm going to give you an overview is an interface, and as some of the talks have been alluding to, interface in optics is interesting. There's also some interesting conceptual interfaces, and in this particular case, I'm going to bring in something which is fascinating in the context of soft matter physics, to a large extent, any kind of soft matter, and also a very interesting domain from optics, which is related to something called a structured light. I am aware of the fact that the majority of the audience here are mainly from, let's say, condensed matter physics background or something related to that. So I'm going to also give a slightly more elaborate overview of what is structured light, etc. If you have any specific questions, clarifications, don't hesitate to pause me and ask the question. So the outline of this particular talk is to just introduce you to some of the questions and the motivations related to the work, what we have been doing. Specifically, I'm going to introduce an interesting concept called as hot Brownian motion and hot Brownian colloids, which has turned out to be a very fascinating concept, which uses some background from optics and photonics and bring it into the domain of some very fascinating concepts in soft condensed matter regime. I'm going to also give a very brief overview of something called as plasmonic colloids, especially in the context of confinement. And I'll also motivate why we can or why we should also study confinement. What is the relevance of that particular technique and mechanism? What new information you can obtain, and what fascinating effects you can extract out of that. Especially in the context of swarms and networks, I'm going to give you some overview of some of the work, what we've been doing, especially at the metal fluid interface. And you'll see some emergence of the processes in terms of the assembly, driven mainly by optical forces and optothermal forces. There's also some very interesting statistics which you can extract out of the interaction between the colloids and light, especially in the context of extreme statistics. I'm going to very briefly touch upon that concept of what is that kind of extreme statistics. I'm going to show you mainly the experimental results, but if somebody is interested in also discussing some specific aspects of the mathematical underpinning behind that, I would be very happy to do that. I will also discuss a little bit about passive colloids interacting with some specific kind of sources. In one particular example, I'm going to show you what will happen if you have an extended thermal source, which is extended only along one specific dimension. For example, a quasi one-dimensional channel, mainly assisted by kind of a mesowire. I'm going to show that you actually can achieve something called as optothermal pulling and also trapping and crystallization of colloids in such kind of an environment. And I'm going to switch from passive colloids to thermally active colloids and ask the question, what happens if you confine them, especially using optical potentials? What is the emergence process? When you introduce linear momentum, when you introduce angular momentum. So these are the two regimes I'm going to look into, especially in the context of spatio-temporal patterns. That is something which is equally interesting. And one concept, which is something relatively new, is the emergence of chiral rotation. I'm going to show you under what specific conditions you actually can study rotation and what really determines the chirality of the rotation, meaning the handedness of the rotating colloids in optothermal potentials, and some prospects and conclusion. So the central questions, what we have been trying to address in my own laboratory for almost now close to 14 to 15 years, is to realize out of equilibrium soft systems using light. Some of the guiding questions are how to influence Brownian dynamics using light, specifically the effect of optical confinement, emergence of spatio-temporal pattern. You're going to also see in a few minutes how that is relevant. What are the implications of Brownian dynamics and pattern formation on statistical properties of light, where you can now utilize soft matter systems to realize new and interesting states of light, especially in terms of what you actually can extract out of that interaction, has turned out to be a very important endeavor in the slightly broader context of photonics, which is mainly driven by the soft matter systems. Mainly, the questions of speckle formation and pattern formations are very fascinating, which is also equally important in information processing. Although I'm not going to talk anything about that, towards the end, I'm going to probably give you an overview of why these questions are important, because it's not just about the phenomena, but you also can utilize that phenomena for something as a functional element. The tools what we have been using in my lab are related to optical forces and torques through optical tweezers and various different platforms. We also try to couple thermodynamics and statistical mechanics with some of the intuition what we can develop. One of the things which I am not going to speak about is the measurement of momentum in the optical domain. As you probably know, the rate of change of momentum essentially leads to the force. You would be able to measure momentum with reasonably high accuracy and therefore extract the forces of interaction between light and soft matter. This is something which is a very interesting topic, but that probably would take another lecture altogether. So therefore, I'm going to just give you a very brief highlight maybe towards the end. But I'm going to surely show you something related to spin and orbital components of light, how they can couple to colloids, and what new things you can learn about it. And of course, tweezers, light scattering, and Fourier imaging are something we have been developing over the years. So this is just a quick snapshot of some activities in my lab, mainly related to soft matter interacting with light. One of the aspects is to ask, how does Brownian dynamics kind of emerge, or rather gets influenced in a specific kind of trapping structures, be it a conventional optical traps, or it can be very specialized traps like optothermophoretic traps or optothermoelectric traps. But they're all mainly excited by some kind of an optical effect. So that is one part of the studies what we have been looking at. I'm going to also tell about how we can trap single nanoparticles in such kind of situations. The other aspect which I'm going to also talk a little bit about is the evolutionary assembly and pattern formation, especially when you bring in the element of absorption into a colloid. Absorption here means optical absorption, and it can lead to some very interesting secondary effects because of that, with optothermal pulling and gradient effects. And this is something I'm not going to talk about, which is the measurement of optical momentum. If somebody is keen on knowing a little bit more, I'll be very happy to discuss. Now, this is one of the very interesting aspects of spatio-temporal confinement. And the fact that you would be able to confine things actually can lead to emergence. So if you now take the kind of confinement, and you look at the various units of matter, all the way from atoms and molecules to planetary systems, you would have a really plethora of effects which are related to this kind of interactions. Be it, let's say, protoplanet formation, galaxy formation, various different specific aspects of biological structures, for example, ants, or even quorum sensing with the bacteria and other kind of elements. To this particular regime, one will have to actually look into what happens if you now look at objects which are reasonably small, and you confine them as a function of space and time. One of the important aspects what you will learn in specific kind of confinements, where you can classify them as external, soft, and hard confinements, is that you would be now able to create confinement which are reasonably soft, so to speak. Optical effects give you that particular soft confinement, meaning you first of all can vary the confinement with reasonable ease, and the effect of that confinement on the soft matter itself is not very what should I say? It's not cruel. It's not going to actually really take the system really out of equilibrium such that it actually can disrupt its structure or something like that. Biological cells, for example, have been studied. For example, some of the very interesting experiments which have evolved in recent times is the confinement of RBCs in an optical trap, or you actually can have dual optical traps and stretch those RBCs. And you would be able to study the structure and formation of various different biomolecules on that kind of a platform. So there are various different effects through which you will be able to study things. But what is of interest in this particular lecture is to ask not only the emergence of dynamic structures, but there can be potentially some function to that particular confinement effects. And that is something I would want to emphasize a little bit more on, where you can also enable some functions through this particular confinement process. So out of equilibrium soft matter systems, essentially driven and confined by structured light. This is what I'm going to mainly kind of define about. The interesting aspect is you actually can not only take the system out of equilibrium through light. I'm going to define what is structure in the structured light, but you actually can also use the same light source, or it can be a different light source, to probe that particular soft matter system which is driven out of equilibrium. Most of the stuff what I'm going to discuss about the soft matter system is the prototypical colloids. We use them because they are extremely well prepared. You really have great control, and they also are to a large extent building blocks of most of the stuff what we study experimentally in the context of soft matter systems. They can actually act like a model systems for various different situations, including, for example, liquid crystals or some kind of very interesting anisotropic structures. What is interesting is also the fact that you will be able to now take this interaction and drive the system into various different dynamic regimes. This is an important point I would want to emphasize on. The fact that you would be now able to take such systems and create situations in which your dynamics actually can be tuned is one of the strengths of this kind of interaction. For example, if you take mean square displacement, which is something probably you would have computed just in the previous session, and you generally take the conventional aspect of Brownian dynamics, the mean square displacement and the time has a specific relationship. The famous relationship which you would probably be associating the Einstein's equation, etc., etc. What is interesting is by playing around with the optical source, you would be able to now take the object of interest either into the subdiffusive or confined regimes, or you actually can drive them into super diffusive or directed regimes. This can be driven, and in the context of, let's say, active matter and such systems, you actually can have a kind of a global source of energy which has been pumped, which is pumping energy into that particular system. And you can also study such kind of dynamic regimes in such systems too. But here we are exclusively driving the system and looking at some specific interactions. There's a lot of work across the globe, including in India, in this particular direction. I would urge you to have a look at many interesting works which are actually emerging in the recent times. I've just noted few, but there are quite a lot of people who have been working on these kind of questions. Although they are not oriented towards one specific problem, but the techniques what one uses is common to various different specific situations. One of the aspects of light soft matter interaction is to look at the interaction regimes. This is mainly driven by the definitions from an optical physics viewpoint. For example, if you take atoms and molecules, you would be able to now utilize dipole approximations, and therefore you can slot them into so-called Rayleigh regime, which is conventional regime in which you would be able to utilize the dipole approximation and compute your scattering cross sections, etc., etc. There is another extreme in which you can use geometrical optics viewpoint, where you can use very well established rules, mainly kind of approximations, which are very effective. For example, if you are trapping a reasonably large cell, or for that matter, a droplet, which is also an interesting prototype to understand light soft matter interaction, you would be able to utilize the general rules of geometrical optics and study that particular interaction. Of interest in recent times is this intermediate regime, where first and the foremost is that there is a variety of structures which neither can be just approximated from a dipole viewpoint, nor you can take a geometrical optics viewpoint. This is where the full electromagnetic interaction has to be utilized, where you have to now solve full wave Maxwell's equation and extract the specific components of the field. And through those fields, let's say electric and magnetic fields, you would be able to extract Maxwell's stress tensor. And from that stress tensor, you would be also be able to kind of extract meaningful information about the forces and torques, what you can obtain in such kind of interaction regimes. Which also means that it brings in some very new and interesting viewpoints, because this is a regime in which Brownian dynamics is also very prevalent. Because the colloids, what you have suspended in the fluid, also has this kind of local kind of perturbations and very interesting dynamics which happens, and you will have to account for all those interactions which are there. It is also a very interesting system to study non-equilibrium statistical mechanics, and there are a lot of groups who are doing this with reasonable efficiency. Now to the structured light. One of the most definitive books written in the history of optics dates exactly about 1,000 years. Al-Hain's very famous book. So optics actually has a very rich history. It has almost 1,000 years of intuition which has been developed. Many of them incorrect, many of them revised, many gave way to new theories and new interactions. But in modern age, what actually has happened is there's so much of interest which has come out because of the fact that you are now able to generate laser beams, and these laser beams can be engineered. This has really created new opportunities in the way you actually can use laser beams and realize new degrees of freedom, because of the fact that light itself actually has various degrees of freedom. This is just a snapshot and the power of light. A simple equation, for example, what is now displayed here, essentially the cos of kx omega t plus phi times a into this particular vector, which is associated with the orientation of this particular vector. You can see that each and every component of this equation has very important effect on the way it interacts with matter. So much so that you will now be able to utilize each and every part of this particular equation and create further secondary effects because of that particular principle. Take, for example, the amplitude. You would be now able to generate laser beams which can emulate some of the astrophysical processes. You actually can really generate huge intensities using laser beams. where you would be able to now create some kind of plasmas, which are otherwise not feasible in conventional situations. That is just one kind of extreme example I'm giving you. What is of interest to this particular talk is to understand that you would be able to now engineer the phase of the beam, and you can create beams which can carry topological signatures. For example, you can create laser beams, as I'm going to show in a few minutes, which can carry topological charges. So now you can create structured lights, which can now carry topological information. And you all know that soft matter systems by themselves actually can carry some meaningful topological information. So this combination of topologies, so to speak, from two different regimes has turned out to be very fascinating, at least to me. And therefore, it seems to be an interesting area of research which is still fertile. And there are some unanswered questions. And majority of the stuff, what I'm going to show you, actually does raise a lot of questions in terms of how to understand the process per se. There's one more way of creating structured light. In addition to, let's say, having just the conventional free space beams, it is to use electromagnetic interactions at interfaces. One of the interface which is of very high interest in the optics community is the interface between a metal and a dielectric layer. You would be able to now generate surface electromagnetic waves thanks to the concept called as surface plasmon polaritons, which are essentially charge density oscillations of electrons at metal dielectric interfaces, mainly arising because of the specific momentum matching condition which this incoming electromagnetic beam has to be satisfying in order for the energy components to actually be delocalized. In other words, if you take a metal dielectric interface, you can now chisel this particular metal in such a way that you can create a small grating at that particular interface. You can have an incoming electromagnetic radiation, and this particular incoming electromagnetic radiation can now give rise to so-called surface electromagnetic waves, of which plasmons is one sub part of this particular interaction. What is very fascinating is that if you now look at the electric fields which decay across this interface, it actually is exponential. Interestingly, this particular exponentially decaying function means that if an object which is very close to this particular interface is subjected to a very large electric field, the moment you step away from this interface to even a small distance, the electric field actually decays drastically. So this is also turning out to be an excellent tool to study interfaces, because majority of the interactions what we are now looking at is happening right at this particular interface. So the interaction volume is reduced drastically. The coupling is also increased drastically. So it has turned out to be a very interesting and powerful way to even detect single molecules for that matter. So therefore, there are various different applications, but I'm going to show you some parts of how these interactions can be used. Because as you know, the moment you have electromagnetic radiation interacting with metal dielectric interface, if you want to satisfy the generalized electrodynamic processes, there is also a ohmic loss, which actually is always there. So you would end up actually having a lot of dissipation in terms of non-radiative interaction, meaning you will actually end up heating this interface. Therefore, you would be now able to create localized heat sources by illuminating such kind of metal dielectric interface. That is something I'm going to show you in a couple of minutes. So you can propagate such kind of signals. For example, you can illuminate, let's say, a silver nanowire, roughly about 100 to 200 nanometers in diameter, and extending over a few tens of microns, or at least multiple of 5 microns, where you will illuminate this particular wire at one end, and you will see the photons emerging out of the other end. This is all mediated through this wire. So you are able to now transport optical information through conduits whose dimensions are smaller than the wavelength of light. Welcome to sub-wavelength optics. Because of the fact that you are now able to transport information beyond the limit of diffraction, this has totally changed the game of how you are looking at optical phenomena. You know, yes. This is made of silver. This black part is the This is silver wire. You fire a laser beam, focus the light at the distal end, one end of the wire, and you'll see that there is light emerging out at the distal end of the wire. Because now you've converted the photon into plasmon. The plasmon is now propagating and reconverted from plasmon to photon on the other end. And this is a very intriguing phenomenon because you are now able to transport information from one conduit to the other. The interesting aspect is you will also have a lot of heating along the way. It is a detriment in some applications, and it is something advantageous in certain applications. I'm going to show you the second part very soon. You will also be able to localize this interaction. Yes, please. Yeah. This is a quasi one-dimensional channel. The width of the wire is 100 nanometer. Yeah. If you solve conventional diffraction equation for that, it should not be allowing any kind of optical transformation or transportation. But here you are able to convert that to another form of some kind of energy dissipation process and reconverting back that information. I should mention that what was promised as an important technological implication via plasmon has turned out to be detrimental for photonic applications. Interestingly, the people who are really utilizing these plasmons nowadays are people who are using it for creating localized heat sources, like photothermal therapy, and you'll also see some kind of optothermal interactions, things like that. So it was envisaged to actually create revolution in nanophotonics, but it has turned out to be an important thing in some other field altogether, including, for example, catalysis, which is also an important area of research, especially when you confine objects to a smaller and smaller scale. So you now can chisel the metal and you can tune the scattering interactions. So I'm just giving you all the background, but the real fun starts now, because I'm going to show you some of the work, what we have been doing using this particular fundamental aspects. Before that, I'll introduce one important piece of work from a group of Wang Chicos and Klaus Croy, which is a concept of hot Brownian motion. Take a particular colloid, and if you take this particular colloid, let's say this is a gold nanoparticle, which is roughly about 50 to 100 nanometers. And if you now have this particular colloid immersed in a fluid, which is now defined by a viscosity eta, and now you ask, what will happen to this particular colloid and its environment if you have an illumination such that if this illumination is now represented by lambda n, given the fact that these particular colloids, which are made of metallic structures and therefore they harbor plasmons, you would now have an associated wavelength of absorption for the plasmon. If you happen to have a specific kind of interaction such that the lambda in is almost equal to the plasmonic absorption, then the amount of heat which is generated in this particular gold particle is very large. Because what happens is it will take this particular system out of equilibrium. The moment you pump in the incoming electromagnetic radiation onto this particular colloid, there is not enough time for this particular heat to be dissipated into the fluid. Therefore, you will end up with a specific situation where this system is always kept out of equilibrium. Unlike, let's say, a dielectric colloid, let's say made of polystyrene or some other particular colloid, if you now do the similar kind of experiments, this particular stuff, the absorption is very low. Which means that the moment you pump in this energy onto this particular colloid, you will be able to dissipate the heat generated in this colloid into the medium which is present around this particular colloid. Therefore, such kind of dielectric colloids equilibrate much faster. Whereas if you now take this kind of hot colloids, they are always at an elevated temperature compared to the bath. And if these colloids actually are in the Brownian regime, then the dynamics becomes very interesting. The crucial question is, how do you understand diffusive processes of such colloids? And a very interesting answer is given in this particular paper. One of the aspects is that the diffusion constant is now a scale diffusion constant, which actually now takes into consideration the scale temperature, hot Brownian motion temperature, and an associated viscosity, which is given by eta HBA, which is the local viscosity around the colloid, which gets perturbed because of this illumination. And accordingly, you will now have a specific ratio of the viscosities, and you will also have this hot Brownian temperature, which essentially can be taken as a specific kind of series with respect to the local temperature, what is already present. This creates very interesting situation because now you have this colloid, as long as it's illuminated, it is out of equilibrium, and it creates very interesting dynamics. This also has been now looked at in the context of thermally driven matter. And one of the interesting aspects is to look at them as microswimmers, which are now at an elevated temperature compared to the other objects. This is equally important question when you are trying to do imaging in your biological systems. There can be agents which will help you to enhance the scattering, the local scattering. And one of the ways to actually enhance the local scattering in your imaging technique is to introduce gold nanoparticles. You would have seen this being extensively used for various different applications nowadays. For example, you can target some particular organelle of a cell where you inject very tiny gold nanoparticles into that particular organelle through specific chemical routes or physical routes. Then what one does is now illuminate that particular colloid and then ask what happens to that particular environment in which the colloid is placed, which means that you have to now worry about these issues in such kind of environment. The consequence of this is that you can create some multiple fascinating effects. Yes, yes. Yeah. Yes, yeah. Yeah, see, in fact, it's kind of connected to the temperature increment. For example, you can have an increment as much as 20 Kelvin, which means that you may actually flip an order of magnitude of the viscosity in some particular cases. Again, that measurement of viscosity is non-trivial. It has turned out to be a very challenging aspect in such kind of environments. But what is measured with reasonable accuracy is the temperature. And therefore, you will see the crucial element everywhere is the temperature. From there, you'll be able to extract some information. There's also a roundabout way of measuring some viscosity parameters through some flow measurements, etc. People have, in fact, Frank Chico's group has done some very fascinating experiments. And there are a couple of other groups who also. Yes. It actually is at the interface. At the interface, the temperature, what is given as T HBM, essentially is at the interface at the surface specifically. So the viscosity is now at the surrounding, and there is specific kind of penetration depth up to which you would be able to associate this viscosity regime. This has been also measured because they do particle imaging velocimetry and other kind of measurements around a colloid which has been kind of held static on a surface, and then you'll be able to look at this dynamics. So it's still an open question to understand what is that regime. But there are certain measurements which have matched very well with the theory and the intuition what has been developed. And with reasonable accuracies, the temperatures have been measured. That gives a little more confidence in this particular thinking. Now, one of the crucial aspects is, now if you take, what is the physics behind this? No? Let's try to understand a little bit more. And this will somehow also bring in light matter interaction into the play. So if you now take the general definition of the power in a specific kind of a light matter interaction, it is essentially given by the cross section times the irradiance. So there are two processes, scattering and the absorption. And if you look at this particular interaction, the scattering, essentially the scattering power is proportional to the intensity, but this is related to the scattering cross sections and the absorption cross section for the Q absorption. This is the general definition, but if you want to really look at it from a matter viewpoint, then you will have to look at the heat power density. So this is the general heat power density, which is associated with the imaginary part of the dielectric constant, right? Times the frequency at which you are illuminating that object, times the mod square of the electric field, which is the intensity. If you take this particular heat power density and take the volume integral with respect to any particle of interest now, you end up getting the total power absorbed. So the total power absorbed now actually can be verified using two independent processes. One is through this particular definition, other is through this measurement. For example, all of you would have done this Beer-Lambert's law and other kind of things. That is associated with the second equation at the bottom. So you'll be able to do such kind of measurements and extract some very interesting aspects. I would urge you to have a look at this book. It's very, very insightful, and you'll be able to learn a lot. Now, what is interesting is, now that you have used light, you illuminated the object. Are you able to now use this to create heat? If you can create heat, can you generate forces and torques using such situation is the question. And the answer is yes. And I'm going to show you how we're going to do this. First is the plasmonic colloids under confinement. And here we'll be looking at a specific question of how to control and probe spatiotemporal fluctuations of this so-called hot Brownian colloids over an extended spatial scale. So you'll now be looking at a lot of particles to begin with. And I'm going to then go to the other extreme of looking at only single particle, because you can learn something very interesting in two different regimes. So this is an experiment where you have a metal fluid interface. You now have a gold metal, roughly about 50 to 60 nanometers in thickness, which is optically coupled to the Dow prism. And this is a fluid blob, which mainly contains the colloids of interest. In this particular case, either silver or gold. And this metal surface can either be silver or gold. Gold is more conducive because you would not oxidize them. Whereas if you use silver, it will generally oxidize at a faster pace. But silver is better in terms of the response function. So depending upon the experiment, you can use it specifically. In this blob, what one can do is you can now illuminate a laser beam and generate a gradient of temperature. Because of the fact that now this particular blob is not confined from the top, it creates some very interesting dynamics. As a function of time, you will be able to now create some specific kind of traps because of the fact that there is a gradient of this temperature. And as a function of time, you'll have more and more particles getting influxed and outfluxed. And you will also be able to assemble some particular structures. Having assembled these colloids, the questions one can ask is, what is the nature of fluctuation in such assemblies? What happens to the light which is coming out of such assemblies? What is the nature of the statistics from such kind of assemblies? And in order to study them, you can either use elastic light scattering or you can use inelastic light scattering. Inelastic light scattering is useful. For example, you can use Raman scattering because of the fact that you don't have to worry about processes like quenching, which is generally the main concern when you use fluorescence and other kind of things. So let's look at the experiments. Now, what you're seeing is an aggregation of colloids as a function of time. They form a larger and larger aggregates, and this is reasonably large in size. These are silver nanoparticles on silver film. So they actually form a very large assembly. As you can see, as a function of time, they fluctuate because of the fact that there's a lot of particles which are coming in and going. You can study them. You can also play around. You can use it to create some very interesting reversible assemblies. For example, you can move the swarm of these particles without any structure on the surface interface. Just by moving the laser beam from one location to another location, you would be able to move this particular swarm. So therefore, you now have reasonably good control over the spatio-temporal kind of arrangement of these colloids. The crucial question is to understand this particular electromagnetic interaction. I'm not going to spend too much of time, but this is a three-dimensional finite element, finite difference time domain calculation to just map the kind of electric fields one expects in various different configurations of such kind of colloids. Now that you have such kind of large electric fields, if there is some particular molecule which is now interacting with this gradient of the field, it is subjected to a very large interaction, which is mainly confined to the interface. So therefore, by introducing molecules into this kind of soup of colloids which are formed, and studying the statistics of the light which is emitted from those molecules, mainly from scattering, inelastic scattering, you'll be able to extract some information about the electric fields which you have in such kind of fluctuating swarms. How do you do that? One uses something called as bianalyte technique and uses a methodology which has already been there in the extreme statistical events. The idea is that you now have these aggregates, and into this aggregate, you introduce two different types of molecule. Call those molecules A and B. When you have these two molecules, which are now in this particular fluctuating environment, the kind of signal what you can generate out of the scattered signal are fourfold or four different kinds. One is that you can generate a signal which will have both signals from A and B. You will have signals only from A. You'll have signals only from B. The other one will carry no signals at all. So you can now see that by introducing specific kind of molecules whose cross sections are very carefully chosen, you would be able to now study the fluctuations of that particular aggregate by looking at the statistical events with respect to these four events which are possible. Cutting a long story short, if those two molecules happen to be, let's say, Nile blue and rhodamin 6G, and if you are introducing them with reasonably low concentration, you would now be able to see signals which are exclusively arising because of one molecule or exclusively arising out of another molecule. Whereas the mixed events actually are less probable. This is in the regime of single molecular statistical fluctuations. So what you will be able to now generate is the spectral signatures, which essentially are coming out of the single molecules which are scattered out of them. If you now introduce more and more molecules, you'll recover back the Gaussian function. And if you look at the statistics very carefully, this is associated with a Pareto distribution. And therefore, there is some very fascinating conceptual connections with these experiments too. Now, you can now play around. Instead of introducing one particular interface, you can now have two specific illuminations. And this generates some very interesting situations. For example, you will now be able to aggregate particles at one regime and another regime. You will also form chains, which are not in direct contact with the direct excitation beams, which means that you will now be able to draw things, and you can orient these lines. Mind you, this is all at metal fluid interface. You switch off the field, these colloids go back into the fluid. So you can play around and go back and forth, etc. You can complicate your life a little bit more and introduce more kind of illumination strategies. For example, this is an isosceles triangle which has been generated. All of you probably be aware of the fact that if you have an isosceles triangle, the point which joins all these three is usually called as an orthocenter. If you go back to your Euclidean geometry, This is exactly an assembly which forms at the orthocenter. Precisely. You can go and measure because there is no illumination. Illumination is right at the 3 points of this isosceles triangle. And you'd be able to now study this fluctuations at the orthocenter. It's a serendipitous measurement. We did not expect it. We just actually had 3 illuminations. And we were just curious to see what is the assembly which can emerge out of it. It turns out that you can form assemblies at locations which is otherwise not directly illuminated from the laser beam. So there is some kind of transport of energy which is happening. And the nature of the transport is not totally understood. Although the experiments have been established, we have been able to repeat it multiple times. Others have also done this experiment. But why is this happening? Because if you look at purely a radiative interaction, it should not really penetrate to such a large distance. If it is purely non-radiative interaction, it should not have directionality, right? Because the temperature essentially is distributed uniformly, so to speak, in that particular regime. So there is something which is very interesting, and we don't know the answer. At least I don't know the answer. I'd be very happy if somebody could also think about this problem. Now I'll just switch over to controlling and probing spatiotemporal fluctuations at a limit of optical resolution. Instead of now looking at this problem of metal surface and many particles, we'll, instead of having a full-fledged metal surface, we'll just introduce one small absorbing element on the metal surface, like a gold particle, make it static, illuminate this particle, and then ask what happens to the particles which are there in the fluid. This is what happens. This is actually an anchored gold particle, and what you're seeing is a dark field video micrography, which we have developed in the lab. And this also has an optical trap superimposed on that particular method. So you are now able to trap the particle at a single location, and you're seeing, what you're seeing is roughly about 200 nanometer gold colloids, which are undergoing Brownian motion. So you'll now be able to trap such colloids, form a small aggregate of colloids, interrogate them for whatever reason you are interested in, and release them back in the fluid, all happening at a reasonably fast time scale. You will also be able to generate this purely because of the fact that you are now creating gradient of temperatures around an illuminated gold particle, which is laid on a glass surface. So this is 3-dimensional heat transfer equation, which has been solved, and you will be able to map the gradients of temperatures along the z-axis and also the other dimensions, the other two dimensions. Again, you can study the fluctuations, which will give you further insight to the problem what I was just mentioning. You can study fluctuations right at the interface of 2 particles. These particles are roughly about 200 nanometers. You can create dimers. For example, there's one gold particle and the other gold particle is now interacting with each other. So people who are now interested in questions such as stochastic resetting, which is a very interesting concept, are asking the question of whether you'd be able to use this as a template to do the setting and resetting aspect of it. Because now all you need to do to reset or set is to switch off and on the field. Because the particle can now hover around, go to a location of interest because of the fact that it's undergoing Brownian motion. You switch on the field, the particle comes back. So you can keep doing this resetting experiment as a function of time. And that is a very interesting concept. So you can do this too. For example, in my own lab, we have been doing this. For example, this is an anchored particle and this is a Brownian colloid. And this is roughly about 200 nanometers. There it is. The laser is on, the single nanoparticle is trapped. We'll switch off the laser. This goes out. And we'll switch on again. It'll come back. And you can do this back and forth multiple times. You can do the cycling based. Now, why is this interesting? This is also interesting because you would be able to now assemble particles. Having assembled, you don't have to actually have that anchored particle always there. Having assembled, you can now transport these particles, take it to a location of interest and deposit them wherever you want, without having to worry about the anchored particle. Anchored particle is assisting in generating the heat. The generated heat would be able to create that optothermal potential. The particles get assembled, and you now use the laser beam to bring it to a different location and release it. This is of interest for drug delivery, etc., and other kind of application. That is what we'll show you now. We'll now assemble the particle. The particles are getting assembled at this particular location. You'll see that slowly, having assembled the particles, we'll start moving the aggregate by moving the laser beam. The anchor particle still remains at the same location, mind you. You'll see the assembly is moving towards the left. The anchor particle here you see the particle hopped from one region to the other. The anchor particle still remains here, but the aggregate is now moving down because the laser beam is moving down. We'll bring it to a different location from the start point and release them into the fluid. And these are finite number of particles. So therefore, there is a reasonable control in the aggregate. And there you go. So this, you are able to now move them around as a function of both space and time. Okay. Now, quantum optics is a buzz. Quantum photonics is a buzz. So there are a lot of people who are interested in looking at whether you can trap objects which show quantum optical properties. And Kasturi Saha's group with IIT Bombay is very interested in nanodiamonds. They're interested in looking at specific signals which actually emerge out of the nanodiamonds. They were interested to know whether we could use our methods to trap such nanodiamonds, because these nanodiamonds are extremely sensitive to probe localized magnetic fields, including within a cellular environment, which means that you would be able to utilize this as a probe to bring it to a region of interest within, let's say, a particular environment, measure magnetic field temperatures, etc. And then you can play around and do a lot of things. So we used our technique where we are able to now trap a single nanodiamond using our technique. So there you go. Here it's trapped. The laser is on. So when you switch it off, it's somewhere there. Once you actually bring it back and forth, you would be able to create this kind of traps. You can trap the object, interrogate them, study the Brownian dynamics of that particular trapped object. Importantly, you can also study the spectral signature of this trapped object. By the way, this is a technique which is an optical trap combined with a dark field microscope with a superimposed EMCCD based photoluminescence detection technique. So it's a custom built setup. I'm going to show you the setup in a while. It took us about 5 to 6 PhDs to generate all these things. I'm just telling it as though it's so easy. It has taken a lot of time and effort. All stories, what you're listening is actually some part of the success story. There's a lot of things which don't work. But tribute to my students who have really put a lot of time and effort in bringing this to the fruition. You can also do the spectroscopic interrogation. I'm not going to go into this. Now I'm going to switch. Can I have 5 extra minutes? Huh? I'm going to finish as soon as possible. Okay. So one of the aspects is to ask the passive colloids interacting with 1D surfaces. What is the effect of 1D thermoplasmonic source? So the idea is that you now have a particular metal, like a silver nanowire. In this case, the wire is actually reasonably thick, roughly about 390 to 400 nanometers almost. You excite one end of the wire with a green laser, and you can see that it gets converted into plasmon, and there's a light which is coming out of the distal end. If you look at the three-dimensional temperature distribution of such kind of situation, you would nicely see that there is a gradient of temperature, which you can generate. What is the consequence of this? The consequence of this is the following. If you now illuminate the wire at one end, and you have, let's say, a colloid which is sitting somewhere slightly away from the wire, at a single particle kind of approximation, or in single particle regime, you'll observe this. They get pulled. Just like a motor protein which is walking on a quasi one-dimensional channel. If you increase the concentration of these colloids, you can study crystallization, where the point of illumination now becomes the nucleation center, and you'll form this very beautiful hexagonal packing. What is interesting is this particular crystallization is sensitive to the polarization of the light which is illuminating this. So if I now park the laser beam with polarization perpendicular to the wire, you will not get any crystallization. So you are now able to control the assembly process by merely playing around with the orientation of the input excitation polarization. This gives you another degree of control in handling this particular system. There's a lot more to it, but I'm going to just go forward and look at the thermally active and active passive colloids. The question is how do thermally active colloids evolve in structured optical potentials and active passive mixtures? This is not going to take more than 5 minutes, so I'll be reasonably on time. One of the key elements is to realize some kind of an optical trap. In this particular case, it's called as defocused laser trap, and ask how do colloids evolve in such kind of systems, especially if there are active colloids, which are light absorbing colloids. So the colloids what we use is actually prepared by a very nice company in Germany, where they can prepare with reasonably high accuracy of doping certain kinds of light absorbing particles. In this case, it's ferrous oxide, which has been doped into a polystyrene sphere, and it's been infused. It's not just on the surface, but it actually is also in the volume of that particular sphere. Now you take such colloids which have very high absorption efficiency of the light which we illuminate. In this case, it's 532 nanometers. This is what happens. If you take conventional polystyrene colloids, and now we compare what happens if you take a light absorbing colloids. Let's look at it. In the conventional case, in the defocused laser trap, you'd start assembling these colloids, and they form a very nice systematic hexagonal packed structure. If you now take light absorbing colloids, you now have a short range repulsion and a long range attraction. So they form very interesting patterns where you end up having this assembly emulating some very interesting structures and patterns. Now, the interaction itself is very interesting because you'll see in our experiments, and this is actually a very kind of very specific and highly sensitive experiment, where we now have the laser spot and we very systematically vary the power of the laser which is illuminating this spot, and look at what happens to this colloid. Okay, see what happens. Now the particle is at a particular region. We systematically increase the power. The colloid slowly goes away from that. This also is an indication of this kind of repulsion because of the fact that the colloids are absorbing that particular thing. You can use this also to orient the colloids. For example, you can have a particular polarization of light, and you have, there you go, from X to Y polarization, you'll be able to flip its orientation. And it's all happening at sub-micron scale. You're doing it at an extremely small scale. So it's a very kind of sensitive experiment you have to do. You can now do a lot of systematic measurements. Anybody who is well versed in the optical trapping would know this is an associated trap stiffness. And because of the fact that it is not just only the optical trapping force, but also an optothermal force. So the trapping stiffness, what you now compute, or rather measure, is kind of an effective trap stiffness because of the fact that there is a heating element coming to it. So therefore, your mean square displacement and other quantities what you have is essentially an effective kind of parameter. And you'll be able to measure those trap stiffness along the X and the Y directions. You can also see that orientation can also be played around, and you can do systematic studies. You can also create some very interesting architectures, dynamic architectures, where you can have a trapped object and a hovering object. And you can now play around with the power of the trapped illumination so that the hovered object actually keeps going back and forth, and you can study the dynamics of that. And you can see that you can measure with reasonable accuracy the mean square displacement, etc., and extract some very fascinating dynamics. You can also orient them. So you can now trap objects which are now interacting with each other, and you again flip the polarization from X to Y to X. You would be able to now reorient these objects. So you can again do the same systematic measurements, and it's a reasonably interesting way of looking at the interaction. But you should be very careful when you're talking about trap stiffness, because these are all effective measurements, as I told. It's not pure optical effect. This is one thing which is something which is very fascinating. If you start mixing these colloids, 2 passive and 1 active, and you now eliminate only the 1 passive colloid, depending upon where this active colloid is sitting in the geometry, you'd be able to now create chiral rotation. So you'd be able to now generate rotation in one direction, and you can create a rotation in a different direction purely based on the location of the active colloid. We have done systematic study of this. We have also done some specific kind of force calibration measurements on this. The active colloid location plays a very critical role. Okay, I'm not going to go into the details, but suffice to say that the location of particles plays a critical role. The last part is, you saw that there can be rotation generated with only linear momentum. You can now have optical beams, as I told, which can carry topological charges. What are those beams? They are optical vortices. These optical vortices actually have a helical wavefront. The conventional Maxwell's equation for a plane wave gives you the specific constraint that the k vector and the E vector and the B vector are mutually perpendicular to each other. You can still satisfy this particular condition, but you can now have your pointing vector not only just moving along a one particular direction, but instead of actually moving in a specific line, this can take a helical wavefront, which means that this particular beam of light can now carry an angular momentum. Depending upon the winding number, which is the number of windings per particular pitch, you can associate a topological charge. Depending upon the directionality of this winding, you can associate the sign of the topological charge. So therefore, the topology becomes very interesting in such situations. So what happens then is you can now create spin angular momentum and orbital angular momentum in such kind of systems, where the particle now can rotate on its axis, or it actually can go around a particular axis, which is defined by the center. So for example, if you look at this is a very nice kind of animation, where you have, let's say, start with an orbital angular momentum whose L value, which is the topological charge value, what I'm talking about, is now -2 and spin -1. You start with this because L plus sigma is now the spin and the angular, the orbital component. Let's see. This is a very nice thing. There you go. You can see this number changes from -3. You keep no spin, so therefore only orbital motion is there for -2. Now -1, because there's a -2 and plus z. If you moment you change it, the directionality changes. So you actually can now play around with both the spin component and the orbital component of the light, and you can really control the directionality of both rotation and the revolution of the particle. And there is very interesting opportunities in this particular viewpoint. This is all done through a microscope system which we have built in our lab for several years. I'm going to show the acknowledgement where I will tell you how many people were involved and etc. later on. Last aspect is to look at these kind of colloids in such kind of angular momentum carrying beams. For example, you can have a topological charge defined as +3. Now for passive colloids, they just create this rotation. You can see, you'll be able to now assemble these particles. You can start looking at this very interesting rotors. But the moment you bring in light absorbing colloids, look at it, what happens. You of course have this fast movement. There is still that repulsion. So unlike this case where there is some kind of interaction, here the repulsion is still maintained. And you'll see that as more colloids join in, that repulsion is still kind of maintained. They don't collapse into a single structure. There is something which is more. Even more complicated aspect, I'm not going to go into details. There is something called as optical binding effect, because you can create electrodynamic interactions by introducing a metal particle instead of a conventional colloid. This creates a very even more complicated kind of dynamics. You can see that they actually rotate, but also there is a repulsion and an attraction which happens. And this is related to something called as optical binding. And people have also generated some very interesting effects using this. For example, they can generate something called as negative torques. It's a very fascinating physical process. For example, you now have a beam which is carrying an angular momentum associated with the direction of this particular handedness, which means that there are now particles which are now trapped in this confinement. So they all start going around in a particular direction. What is interesting is now you can have a test particle which will try to join in from the outside. And this test particle does not have the same absorption characteristics of this particular particle. The test particle starts actually moving in the reverse direction. So this process is also called as negative torque. The dynamics actually is not worked out completely. It's a very, very interesting problem, because the electrodynamics and also other interactions have to be studied in detail. So a lot of things what I've talked about actually has been culminated in some of the articles I've written. This is a roadmap article where I've talked about how to trap and look at particles which are extremely small. There's also a recent special issue on nanophotonics, which is to bring in some things which are done within India and look at what are the interesting questions which we are trying to understand. So all these articles are on archive. So please have a look at it. And if you are interested, you can go a little deeper. Let me finally give you two perspectives. One is that we can look at this problem from a statistical mechanics viewpoint, where you look at this dynamics. What I have not talked about, but it is very fascinating, is to invert the problem. You take some particular scattering token. The scattering token can be a soft matter system. You can now have laser illumination and you can generate speckles. And these speckles actually can carry information, which are now encoded in this soft matter dynamics, which means that you can do optical processing, optical information processing using this kind of experiments. And you can also do precise rotation measurements, which are equally important for various different technologies, etc. But it gives a lot of things to think about, and it makes it fascinating. Finally, I will end with this very nice analogy by P.W. Anderson. I'm going to quote from More is Different. The constructionist hypothesis breaks down when confronted with the twin difficulties of scale and complexity. The behavior of large and complex aggregates of elementary particles, this is also true for colloidal particles, it turns out is not to be understood in terms of simple extrapolation of the properties of a few particles. Instead, at each level of complexity, entirely new properties appear, and the understanding of the new behavior requires research which I think is as fundamental in nature as any. Soft matter physics does this, in my opinion, at least. And more importantly, to take more is different, it also makes it wonderful. So finally, let me acknowledge, this is probably the most important slide, because this is to do with the people who are associated with the work. There are a lot of postdocs who contributed, especially the structured light viewpoint. Among the 11 students, at least 7 students played a critical role in building that microscope. It's just like this Gaudi's architecture. It is always under construction. So I really am thankful to all of them. Also undergrad students who played a very critical role. Rohit was one of the main person who started a lot of activities. Now he's a faculty at Birmingham. And Sunny Tiwari did a lot of nanoparticle coupling and dynamics. is now in Oxford. Rahul and Eksha did the experiments on this light absorbing colloids, especially the rotation experiments. Ashutosh did a lot of work on single particle trapping measurements. Sumant is setting up some experiments related to liquid crystal droplets. I have not talked anything about that because their problem becomes even more complicated because the anisotropy comes into picture. And as we have already heard, there's a beautiful physics behind that particular concept. I should wholeheartedly thank my colleagues, Vijay, Apratim, and Deepak. I've got a lot of insights and very interesting feedback from them. I really value that. Funding from various different sources. And the most important thing, thank you all for your attention. Thanks. So you can explore a lot more on my blog and the YouTube channel. There is also lectures and other things. Please have a look at it. And I'd be happy. I'm around for the whole day today. Unfortunately, our semester has started. So therefore, I will not be able to spend a lot of time. But I would be very happy to interact today.
Thank you very much, Professor. This is a really nice, cool things that you've shown us. Since we're already past 5, we have time for maybe 1 or 2 questions. And then maybe we'll be around today.
Yeah, I'll be around. Sorry, I took a little longer.
That's okay. And then just come and ask you.
Yes.
So maybe you told what I missed. So why the active particles repel when in the field?
Yeah, what happens is once you eliminate these particles, there is now an absorption associated with these particles. There are 2 forces at play. One is the optical potential, which is the gradient of the intensity, which creates this gradient force, which is attractive in nature. Whereas the heating effect tries to repel it. Now it's a combination of these 2 forces. So neither is the force too weak to repel it completely, neither is it too strong to bring it into the region of interest. So now there is a kind of a dynamic equilibrium which is established. So it finds a spot where both things are satisfied, so to speak. And yeah, this is something experimentally also measured. And you can also do the energetics. And we have also seen in molecular dynamics the kind of simulations one would be able to.
We have another question.
Yes, please. Yeah.
Hello. Sir, in your slides, you showed optical tweezers. The gold nanoparticles were aggregating to another particle, which were trapped with optical tweezers.
Yes.
So you said the dimension of the particle was 250 nanometers.
Yes.
Fluorescent particles?
Can you repeat what is?
Are they fluorescent in nature?
No. In fact, the imaging technique for all the metal nanoparticles is through dark field, which means I'm using the scattering from those particles. The fluorescence is not prevalent there. They can be photoluminescent, but that is a very weak signal. Yeah, that's a good question. In fact, what you're looking at is not the exact spatial extent of the particle. In fact, that is the technique behind the dark field imaging. In the dark field imaging, what one does is you now have a scatterer. Okay. And if this scatterer can be roughly, let's say, even a 50 nanometer scatterer, gold nanoparticle. The technique is based on the fact that you now illuminate this particular particle at an angle, let's say theta in. Okay. Once you actually have this illumination, this light is now scattered in all different directions. What one does in dark field scattering is create a specific kind of an imaging method such that the angle at which you are now collecting this light from the scattered object, and if you call that particular angle to be theta out, the theta out is less than theta in. And how do you do that? You actually use a ring kind of a illumination such that the light which is illuminating is only at a particular angle, which is much larger than the collection angle. So what enters the detection channel is only the scattered light. It doesn't contain the illuminated light. So what you are now seeing in those videos and images are particles which are scattering light. the light which is scattered is still diffraction limited. But the advantage is that it is now coming from a background because the light is scattered only from these particles. And that's the reason why it's called dark field image, because your background is dark and only the scatterer gets illuminated. So if you take the particle to be much smaller, where the scattering efficiency keeps lowering, then the scattering efficiency keeps going down and you'll not be able to detect it. It's a very powerful technique to study scattering objects. It's called, you can look up, I'll be happy to actually give you more source. Yeah, Santan, yes. I have time. Yeah.
Maybe people have to take the 5:15 bus is gone.
Oh, boy. You have the pleasure of staying back at ICTS, thanks to me. Yeah. Yes.
I was wondering that the range of that potential, that optothermal potential,
Yes.
that is like not very large, right? So like if
Exactly.
you reset it, the length scale is quite small.
You're right. In fact, what is interesting is, see, it is when we call something as optothermal potential, it is optical potential plus a thermal component. So which means that there is still an optical trap there. So that's the reason why colloids do get attracted at the first place. Once they come and try to actually interact with the location of interest, then suddenly they find that there is a particle which is now heated up much larger than its local environment. So they don't collapse into that region of interest. So therefore, there is some interesting dynamics which happens. It's an important question because it's not purely only thermal, which means that you will then have to worry only about the heating. Then you can as well just heat it at a location. The optical trap is superimposed with a thermal trap. That is the combination effect what you're now.
Okay, thanks.
Question.
Yes.
What was so surprising about the chirality that emerged out of the three particles, out of which one was active? Because you would expect any anisotropy activity with one end pinned will give rise to chirality. So what was surprising about
In fact, I did not show you the control experiments. In fact, I have it. In fact, I will not put it. In fact, since you asked it, I have to tell it. You actually can do the experiment. This is something which we have done the experiment with. I take 3 passive particles. No rotation. I take only active particles. Similar situation. No rotation. I now take active passive combinations with a structural symmetry. No rotation. So there are situations in which you don't get rotation also. The conditions under which they undergo the rotation is very specific. The rotation emerges purely because of the fact that you have specific kind of heat distribution in that particular region. The directionality of the rotation is associated with the particle's position.
But does it not mean that it depends on the anisotropy of the cluster?
It does. That's exactly what is happening because it mainly depends on the anisotropy of the temperature distribution.
Okay.
As long as that is satisfied, and that is exactly what we prove in our experiment. Because you will still have, for example, you can take structurally asymmetric structure, but compositionally symmetric. You don't get rotation. That's an important question. Sorry, I could not show all the data. In fact, we do a systematic measurement in recognizing what exactly is the one which works and which does not work. It's an important question. If you're interested, I will be able to show you more data.
Thank you so much
Thanks.
for also answering all our questions. And thank you, everyone.